Okay, thank you very much, and I'm really glad to be here, and of course to discuss about science. So it's very good. I will discuss with something which is extremely well known, Rayleigh-Benard-Marangoni, but I guess I will discuss about this later on because there is some point which has been missed for a longer time, and I would like to emphasize that I am also collaborating with some Indian colleagues. This is Diwakar Seyanur from GNCASR, and he's a master student Mishra. And I have right now in my lab a student from IIT Kanpur. He's a PhD student, and so this work has been done by himself. So I am presenting his work right now. The results have just come last week, so I hope that everything will be correct. Okay. So it's Rayleigh-Benard-Marangoni convection in a two-layer binary fluid system. So before going further, so I will introduce you something which has nothing to do with Rayleigh-Benard-Marangoni. It's a Faraday instability, and of course, I guess Dipin Pillai is here. He has introduced this extremely well yesterday. So I won't go into details about this, but I will show you why I am talking about Faraday instability. So I have some collaboration with Professor Narayanan from University of Florida a long time back, and Farzam Zouessiag from University of Lille. And so this was also a PhD thesis from Vibor Jajou. He's from IIT. So, okay, so I'm going to show you some experimental results which has been conducted by Farzam Zouessiag in Lille. So on the left, you have the immiscible case. Well, the frequency is something like this, and amplitude, I don't talk about the values, but you need to be careful about the temperature. So this is at ambient temperature, and this one is for miscible case. So when you increase the temperature, you are coming back to some kind of consolute temperature, which is the critical temperature, where you have the two fluids which are going to be miscible. So this is a binary fluid, FC72 silicon oil, and I will just try to show you if it's working. Yeah, so these are, of course, Faraday instability. So you have a container which is contained by the two fluids, and you are vibrating vertically. So you have seen Faraday waves. It's harmonic for this immiscible case, and as you can see also for the miscible case, of course, everything is mixing quite well, and it's subharmonic. So we have done an analysis again a long time back, and everything has been published on that. And so we have also gone through this phase diagram. This is the vibration amplitude as a function of frequency, and we have characterized all the modes A, B, C, which are given here below. So this is all the points are experimental points, and you have also a theoretical which is based by an excellent paper by Kumar and Tuckerman. So it's everything is done over there, and so we have reproduced the results from Kumar and Tuckerman, and the results are quite, I mean, matching quite well. The stability diagram going towards the temperature. So as I was telling you, so this is the temperature which is coming closer to the consolute temperature, which is the critical temperature. So we have again done the experimental and theoretical work, and so it's matching quite well. I will not go into details about all the modes, but the question which we are asking by ourselves is that can we go continuously from immiscible to miscible? So this was the question which I was asking by myself, and so I discussed this with Ranga Narayanan and Farzam Zouessiag, and they were both saying, "Oh, I don't know how can you do it theoretically." So this is the question challenge numerical. So we have gone through a numerical phase field modeling, and I will come back to this with a vanishing appearance of an interface as we go continuously from subcritical, supercritical to supercritical subcritical states. So this has been done by a colleague from Germany, Michael Besteron team, collaboration with BTU Codebus. So we have, of course, published a paper on that, but they have also published a paper in 2003, which is excellent paper. So I guess everybody wants to go through this. It's going to be very nice because I was approaching Michael Besteron because he was an expert in phase field modeling. So we also did started some phase field modeling at that time with Diwakar Sharma for a PhD. And so the phase field approach delivers a continuum thermodynamic model which can treat multi-phase problems. So I guess most of you might know about this. So you have an auxiliary variable phi, which is the phase field, is added in the usual set of set variables in order to provide an explicit indication of the composition of the system. Okay, and so the free energy density here, so this is, I am highlighting this in blue. So it depends not only on phi, but also on the reduced temperature. So this reduced temperature, you need to pay into attention of this. This is Tc is the critical temperature, so where you have the miscibility of the system. And so what we did with Michael Besterhorn is that we have plotted, of course, the Faraday waves, which have been explained by Deepin Pillai yesterday. So these are the Arnold stones. Of course, all these cases which you are going to see on the left are for r equal to 1, which is the immiscible case. So I will come back to this later on. And so only this case is for r equal to 0, 1, so it's going to go closer and closer to the critical point. And so if you can compare this one with that one. Okay, what we can see is that the wave number is becoming increased, so the wavelength is going to decrease. So I'm just going to show you. So yeah, this is the definition of R, and I will come back also to this later on because this is an important parameter. R is a function of theta. Theta is T minus Tc over Tc, and I will not go through too much of details here right now. So we have just shown here the evolution. So what is the case here? So we go here times to times. As time is increasing, go like this. So immiscible R equal to 1 till 570 seconds, so it's here. And then we switch on continuously R equal to 0.1. Okay, so what you can see, of course, the wavelength is decreasing. And I guess I have a movie, I'm not sure if it is going to work, but the movie is too slow, so I will go a little bit faster. This is, of course, done by the code coming from Michael Besterhorn. I'm not sure if I can go faster. So you have the Faraday waves at the beginning. So see the time here, I'm not sure if you can see 2.9, 3, and so on. So at 5.7, we are going to switch on the miscibility. I guess it's going to come right now, but I will stop because otherwise I will not have too much time to finish what I would like to talk. So right now, yeah. So now we are switching on this R equal to minus 0.1. So you are completely in a miscible state. So you can see the wavelength which is going to decrease. And then of course it's going to mix and it's going to be stable. So at some time we are going to the stable case. Going back to our problem right now, Rayleigh-Benard-Marangoni. So I will start with something which is extremely well known in the mantle. So you have, of course, here the lower mantle, upper mantle, and you have a transition zone. So this is the basic idea, but you have also many applications, but I don't have time to go too much to applications. But you need to, of course, go through the definition of these two numbers, Rayleigh number, of course, which is dependent on the temperature gradient. And you have Marangoni, which is sigma theta is the derivative of temperature as a function of temperature. I mean, a derivative, sorry, of sigma as a function of temperature. Sigma is the surface tension. I will come back to this later on. I would like to emphasize on this, again, excellent paper from Johnson and Narayanan in 1997. They have explained several scenarios. And I was not aware of this kind of scenario, so I was thinking that it might be a good idea to go through it. So there is, you hit the bottom plate, and of course cold plate, so it's some kind of Rayleigh-Benard configuration, but you have also interface. So if you take into account the surface tension effect, so you will have Rayleigh-Benard-Marangoni, otherwise it's Rayleigh-Benard. So this is what we call lower dragging mode. If the height of the lower layer is larger than the upper layer, so you have, of course, what we call the lower dragging mode. So the lower dragging mode means that this one is going to, how to say this, it's going to imply the motion of the upper layer. So I will just go through it regarding this paper. So they have taken silicon oil air. And so what we can see here is that, of course, the velocity, so this is the velocity and this is the temperature. So the velocity of the lower layer is, of course, very high. So this is why it's dragging the upper layer. So you have also another scenario. I will go very fast right now. Upper dragging mode is the inverse. So it's almost the same, but of course, right now, the upper layer has a higher velocity. And you have something which is completely well, new for me also, is that what we call his mechanical coupling. So if the upper and lower layer have the same height, so you will have some kind of mechanical coupling because it's a constraint which is going to be continuous. And so it's exactly the same, so the velocity is almost the same magnitude. And the last one, which I was not aware of at all, is that which we call thermal coupling. So the thermal coupling is that, of course, you have rolls which are going in the same direction. So the problem is that there is some kind of problems of continuity of stress. So you will have some kind of rolls, eddy rolls, which are coming at the interface. So this is again approached by this. So see, the temperature here is almost zero for the mechanical coupling, but here you have existence of a temperature gradient at the interface. So this is the scenario, and what we are trying to do here is that there is no literature available to explain the physical intricacies and nuances of the flow when the binary flows goes to mechanical thermal coupling. I will come back to this. Okay, so I will just go through very rapidly about the phase field method. Some of you might not know about this. So I'm just giving you some kind of sketch here. You can look at this, and it's very, very easy to look at this. But I will probably go much more on the free energy formulation. So in the free energy formulation, this is the F. So you have two parts, the bulk. I will come back to this bulk later on. And you have the interface. So interface is, of course, given by this gradient of phi, which is extremely important here. And so you have also some additional parameter. So what we have done with Michael in the paper is that we have added this term Rp and Rq. R, as you remember, it's a T minus Tc over Tc. And H is the Heaviside function. So it's, of course, going to 1 if R equal to 1, and of course 0 if it's R equal to 0. The bulk part here, it's some kind of double well potential. So I guess it's classical. You need also something regarding, because this is going to come back to the momentum equation. So I will just introduce here the chemical potential. So the chemical potential is, of course, the functional derivative between of F as a function of phi. So this is the solution for this chemical potential. And I have not introduced here right now. This is the free mixing free energy, which can be determined in equilibrium by this aspect. So, in fact, you don't have an interface like a VOF, level set, or whatever. So you don't have an interface. So you don't need an interface. So you have the surface tension, and I will come back to this. I guess it's going to come back later on. You have two parameters, surface tension and epsilon, which is going to be the diffusion layer thickness. Okay, and this is coming from thermodynamics, and it's very easy to get these two parameters. Well, okay, so these are the governing equations. So everything is classical, I would say, except this mu grad phi. So mu, as I told you, it's a chemical potential, and phi is your phase field parameter. And so what we have used here is this is the surface tension force, as I already discussed, and we have used the Boussinesq approximation. So Boussinesq approximation, of course, it's dependent on all the parameters. I will come back to this beta 1 and beta 2, which are fluid number 2 and fluid number 1, as a function of phi. And also you have also rho, which is dependent on phi. I will come back to this later on. So you have, of course, continuity equation, momentum equation with the Boussinesq approximation, and you have also the phase field evolution equation. And this is just something related to what I have discussed just before. And you have gamma, which is here, the mobility. Okay. So there is another parameter which is coming back to the mobility, and I will not have time to discuss about this because numerically it's not very easy. And you have the energy equation, which is classical. Of course, this is coupled through phi, and you have all the parameters who are defined as a function of fluid 1 and fluid 2, rho, density, dynamic viscosity, conductivity, and heat. So I would say the system is quite trivial, but I guess we have to be careful about not forgetting all terms. And I will come back to this. So linear stability analysis, what we have done, of course, we have this configuration, as I told you. Fluid 2 is the upper fluid, fluid 1 is the lower one, and you have the So these are all parameters for the dimensionless analysis. Of course, everything is based on the layer 2. Okay, so H2 square over, this is the thermal diffusivity and so on. And you have a number of parameters, but I will much more act on this Rayleigh number. So you have a Rayleigh number, Prandtl number, and this is the Galileo number, and you have a Mach number. Mobility number. Sorry. Marangoni number. Sorry, I forgot. And you have so what we do here for the linear stability analysis, we perturb with phi prime. And we have all the base state here. Of course, U base state is 0. So this is a classical analysis. I will go a little bit faster. So these are the equations at the end, the perturbed equations, momentum, phase field, and energy. So we have everything here defined. So you have the surface tension forcing, which is coming through this mu prime. You have the body force variation order parameter, and you have also the last one, which is the body force due to temperature variation. Okay, and so in the phase field equation, you have also this dimensionless mobility parameter, which is defined here. Okay, you have also another parameter here, which is the inverse of capillary number, which is coming here into picture. As I already discussed about Rayleigh and Prandtl and Galileo. So we are expanding this in normal modes. It's classical one. I will go very fast here. So you have what we have done is this is coming from GNCASR also regarding the spectral code. So we have this matrix system to solve. It's a classical, I would say. And the variable are specially discretized using Chebyshev pseudospectral method. And we are using the Gauss-Lopato points in order to, of course, take into account all interface and boundary conditions. Okay, how long time do I have? Because I need to go for the results.
You can take 5 more minutes.
5 more minutes. Okay. So regarding the results, this is much more important. You have, of course, so you have to be careful. This is all the phi hat and so on is coming from this. So these are, of course, what is in front of the exponential. So these are the boundary conditions. I will not go into details about this, but what I need to emphasize here is that if we have a pure immiscible state, R equal to 1, to relatively miscible state, so we have not gone to 0. So we have gone to a very low value, which is 5 × 10⁻³ . And so there is another point which is very important here is that rho beta, which is beta is the thermal expansion coefficient, kappa T is the thermal diffusivity. So the ratio should be 0. I would say little small, because the value of this ratio is out to be far from unity in order to observe the oscillatory mode of convection. So I will come back to this oscillatory mode of convection, but I put this in bold in order to emphasize on that. And there is another thing, is that properties are chosen such that unique values of critical height ratio, which is defined here, are obtained. This height corresponds to equal Rayleigh number in both layers. Okay, so these are the two conditions in order to observe oscillatory modes, and I will come back to the results just right now. Okay, so this is the neutral curve. So we have not gone through too much because these are recent results. So what we have here is, of course, Rayleigh number for fluid layer 2 as a function of the bottom height layer. As I was telling you, you have the lower dragging mode, upper dragging mode, and so on. So this is for different R, and so this is only the case for Rayleigh-Benard right now. I have not taken into account the surface tension. So what we can see here is that, of course, the curves are almost the same, but what we can see here is that as if you go, for example, height of 0.3, so when you are reaching r equal to 1, so r equal to 1 seems to be much more unstable than r equal to 0.05. Okay, what is the reason? Of course, so what we are seeing here is the upper dragging mode, top dragging mode, and you have also the bottom dragging mode. You remember, as upper dragging mode, this means that the lower layer is the height is smaller than the upper layer. So this is what we call lower dragging mode, and you can see here something strange happening here. So this strange thing which is happening here, this is what we call oscillatory mode. So it's between mechanical and thermal modes which are going to appear here. So just to explain you exactly how this top dragging mode, I will just focus on this top dragging mode. So for example, I'm just giving you a qualitative sketch of this fluid layer. So R equal to 1, you have of course an interface which is extremely thin. So it's a pure immiscible state. And so these are the two thermal expansion coefficients. So R equal to 0.1, I just emphasize on the fact that it's the interface is very large. So this is the mixing layer. So beta is decreasing. So in fact, this mode, this is why it's much more unstable, much more, not much more, but it's more unstable than the case of R equal to 0.1. So this is just to explain why you have this kind of curve. It's the same for the bottom dragging mode. Okay, well, this is just a conclusion, but I will not go through too much of details. So the question is that many people were asking that, okay, this is some kind of completely analytical solution. Do you have some real case? So we have done a real case, silicon oil FC72. And so we have this, but oscillatory mode it's almost disappearing. There is no oscillatory mode. So, but as soon as you are taking the real properties, the rho beta is 1.2. So it's becoming almost equal to 1. So there is no oscillatory convection, which we have seen here. And the peak of the curve was found to shift rightward as the miscibility increased. The peak here, I'm talking about the peak here. Okay, so this is one fact, and this is the only thing I want to say here about this. Okay, right now we have to put some more complexity here. So we are going to put Marangoni. Okay, if you are going to, of course, increase the Marangoni, energy and continuity are almost the same as Rayleigh-Benard. Okay, in the momentum equation, what we have right now here is the effect of surface tension. So I will not go through all the details, but this is this d gamma, the mixing energy. So this is the mixing energy as a function of theta. So this is the interfacial mode due to thermal induced variation in free energy, mixing free energy. So you will have an additional dimensionless number, which I have noted here. I told to my student, why are you noting this? Why? It's inverse bond number as a ratio of Marangoni to Rayleigh number. So it's dependent on this, of course, mixing free energy as a derivative mixing free energy as a function of theta. So you have the phase field equation, it's the same, almost the same. The only thing it's changing is the mixing free energy as a function of theta. So I guess this is going to be my last slide about the results. So what we have done here is, of course, this is the Y, which is, as I just introduced, effect of Marangoni here. So this is one value of Y. And this is, of course, the case of rho beta kappa T 125, in order to see if there will be some oscillatory mode. For the complete immiscibility, R equal to 1, no oscillation. Okay, and when R decreases, same as for Rayleigh-Benard, exactly the same as Rayleigh-Benard. But you have oscillatory mode of convection for partial miscibility case. So you can see it barely here. So say there is some small oscillatory mode. So what we try to do is, as a function of Y, so it seems that, well, nothing is changing. So a binary fluid system approaching the upper critical temperature loses the definition of an interface. Therefore, the Marangoni component of correction becomes insignificant, and the onset is purely governed by Bayes' effect. So this is the results which have come last week. So I am just a little bit, we are just investigating again this problem right now. Finished. Okay, so I'm not going to conclude, but I'm much more going to see perspectives on that. So we are developing a non-linearized, customized phase field spectral code, and we are also trying to have something with, I will come back to this, with open foam, which is called interface foam, and this is in collaboration with, again, another German team, Darmstadt. So we will see this. An experimental setup, so Diwakar is extremely active in GNCSR. He has also a setup which is built, but of course the results are not right now. And, it's in construction, and I guess the setup is there, but they have some problem with laser, but I will not go into details on that. But this is right now we are doing this. So I was thinking that probably investigation of microgravity might be also interesting regarding the effect of Marangoni versus Rayleigh-Benard. And we are also planning to develop Rayleigh-Taylor, Kelvin-Helmholtz, Rayleigh-Plateau, because I really like instabilities as a function of R. And this is in collaboration with my colleague Jean-Pierre Delville in Loma. And we have submitted again a project which is called ANR-DFG with Germany and France in order to see if we can take into account this pressure radiation term. Thank you very much.
Long live India and France friendship.